Okay, let's unpack this. The internet is vast, messy, and constantly changing. Now imagine trying to build an AI agent that can not only find information there, but actually understand it, reason about it, and take complex multi-step actions like a human would, browsing dynamically to answer your toughest questions.
Yeah, that's a huge challenge.
It really is, and that's the challenge at the cutting edge of AI today.
And that's precisely what we're diving into. We've got a stack of source material today, everything from a high-level briefing doc and excerpts from the research paper itself,
A timeline too, I see.
a timeline tracing related work, and even a study guide breaking down the concepts. They all point to this innovative new system called WebDancer.
WebDancer. Okay, so our mission then is to synthesize all these different viewpoints, kind of pull out the core insights, and figure out what makes WebDancer's approach, well, significant. What's the key problem it's trying to solve, and how does it do it differently?
Right. Think of this as your shortcut to understanding the latest developments in building these autonomous web agents.
Got it. So the core problem, where do we start?
Well, the core problem, as highlighted across our sources, is really the difficulty in creating agents that can handle deep information seeking, in the real world web environment.
Not just simple lookups.
Exactly. Existing systems, and you see this in the timeline with some earlier prototypes, they often stumble. They lack the ability to perform complex multi-step reasoning integrated with browsing actions across dynamic websites.
So it's not just about having a powerful language model, it's about teaching it to act intelligently in a browser.
Precisely. The briefing document really emphasizes this gap. Existing agents might be okay at simple lookups, yeah, but they struggle with tasks needing sequential actions, adapting to different page layouts, or synthesizing info from multiple pages discovered over a long browsing session.
The study guide mentions that too, right? About executing long trajectories.
Yes, it reinforces that, noting the lack of agents capable of reliably executing these long, complex trajectories of actions.
What makes building that capability so hard? Like, what are the specific hurdles?
The sources point to a few fundamental challenges. Firstly, getting enough high-quality browsing data. Data that reflects complex, diverse, sort of human-like interactions and reasoning. Most available data is just too simple.
Okay, data quality is one.
Secondly, generating and crucially curating those reliable multi-step action sequences, the trajectories we mentioned that you need to answer complex questions.
Making sure the steps are actually good steps.
Exactly. And thirdly, training agents in a way that lets them generalize effectively, so they work on new, unseen websites and handle dynamically changing content. The web isn't static.
And WebDancer proposes a systematic approach for these exact challenges. The paper calls it a novel, systematic pipeline and a cohesive paradigm.
That's really where WebDancer tries to distinguish itself. It's not presented as just an incremental tweak. It's framed as an end-to-end structured methodology, really focusing on the data creation and the training strategy.
Okay.
And it breaks the problem down into four distinct stages that kind of build on each other.
All right, let's walk through that pipeline. It starts with stage one, constructing diverse and challenging deep information seeking QA pairs. So, data first.
Correct. The primary hurdle is the training data. You need examples of difficult problems and how to actually solve them using web interactions.
Makes sense.
WebDancer's innovation here, and the paper goes into detail on this, is in synthesizing data that specifically demands multi-step reasoning and interaction, really pushing beyond shallow, simple queries. They aim to increase both the volume and the depth of multi-hop reasoning required.
How do they engineer that depth? The sources mention two methods, CRAWLQA and E2HQA.
Right, CRAWLQA simulate realistic browsing. They start with authoritative sites, think ArcSave, Wikipedia, GitHub, places with dense information. Then they recursively follow links, collecting content.
Like digging deeper and deeper into a site.
Yeah. And then they use an LLM, specifically GPT-4o as mentioned, to generate diverse QA pairs from all that content they collected. This helps capture the richness of information you'd find by really digging into a website.
So maybe exploring related articles on Wikipedia and then generating questions that force you to pull info from a few different pages you found along the way.
Precisely. It generates specific question types like calc, multi-hop, and intersection, which inherently force the agent to look at multiple places or synthesize information.
Okay, that's CAOWLQA. What about the other one? E2HQA, easy to hard QA.
Ah, yes. E2HQA is highlighted as a core data innovation, and it's pretty clever. It uses what they call a reverse construction strategy.
Reverse construction, so starting simple and making it hard.
Exactly that. They begin with simple, easy QA pairs. Then, using LLMs, they iteratively pick out an entity in the question. They search for info related to that entity, get some new facts,
Okay.
and then use that new information to rewrite the original question, making it more complex, requiring more steps.
Ah, like the example about the Frank Rosenblatt Award recipient.
Exactly that example. A simple question. Who received the I.E. Frank Rosenblatt Award in 2010? Pretty easy lookup, right?
Yeah.
But they might select Frank Rosenblatt, search, learned he worked on AI and perceptrons, then they rewrite the question, weaving those details in. In 2010, Who received an esteemed award named after a technology pioneer known for work on perceptrons, honoring their significant contributions, something like that.
Wow. Okay, so now you have to figure out who the pioneer is first, then find the specific award named after him, and then find the recipient for 2010, possibly for work related to perceptrons.
Right. It dramatically increases the required reasoning and search steps.
But, and this is the clever part, the original answer is still valid. It just makes the path to get there much harder. It preserves correctness while boosting complexity.
It does, and this data synthesis is foundational. As the study guide points out, the quality of your training data directly limits what your agent can do. These methods are designed specifically to break past those limits.
Okay, so stage one gives them the challenging questions and the content. Stage two is sampling and filtering agent trajectories. This is about generating the steps the agent should actually take to answer these questions.
Right. You've got the hard questions, but how does an agent actually answer them by interacting with a browser? This is where the React framework is central.
React, reasoning and acting.
Exactly. Tying together reasoning, thought, and action. The agent follows a cycle. Thought action, like search or visit a page. Observation, getting back search results or page content. A sequence of these cycles forms a trajectory.
And they use LLMs to generate these trajectories, these step-by-step plans.
Yes, they sample these processes using powerful LLMs. They mention GPT-4o for shorter reasoning chains, what they call short COTS, and larger models like QWQ Plus for longer, more complex chains, long COTS.
But just generating them isn't enough, right? The briefing doc mentioned models can hallucinate or be inefficient.
Absolutely. Simply generating trajectories gives you raw material, but it might be messy. So filtering is essential.
Critically important, I imagine.
Totally critical. These sample trajectories go through this rigorous three-stage funnel-based filtering framework. Think of it as a quality control system to make sure the training examples are actually reliable and useful.
Okay, 3 stages. What are they?
First, validity control. Basically, they just toss out any trajectory that doesn't follow the proper React format. Simple housekeeping.
Makes sense. Keep it clean.
Second, correctness verification. This is key. They only keep trajectories that actually lead to the correct final answer for the question.
How do they check that automatically?
They use an LLMS judge. Essentially, they leverage another powerful model, likely something like GPT-4, to evaluate if the final answer derived by the trajectory matches the ground truth answer.
So using an AI to grade the homework of the AI trying to learn.
Pretty much. And third, quality assessment. Even if a trajectory gets the right answer, it might be super inefficient, like visiting the same page 10 times. So this stage uses other criteria like limits on the number of actions, checks for redundancy, making sure it stays on task, logical flow to further filter for high-quality, efficient paths.
Wow, that filtering sounds quite involved.
It is, and this multi-stage filtering is non-trivial, but really essential for producing that high-quality, clean data needed for the actual training steps.
That makes total sense. You need clean, effective examples to learn from. Which brings us to stages 3 and 4, the actual learning pipeline.
Right, and this is another area they highlight as innovative. Their two-stage training approach. Stage 3 is supervised fine-tuning. That's FT.
The cold start? I remember seeing that term.
Precisely. The model is initially trained directly on those high-quality filtered React trajectories they curated in Stage 2. The purpose is, cold start. It's about teaching the model the fundamental behavioral paradigm.
Like how to dance the React steps.
Exactly. Alternating thinking and acting, coupling thoughts with actions correctly, sticking to the format. It initializes the model's basic agentic capabilities.
Okay.
And there's a technical detail mentioned in the paper. They mask out the loss from the observations during SFT. This helps the model focus purely on learning the desired thought-action sequence generation without getting confused by external feedback at this initial stage.
So SFT teaches it how to behave like an agent based on these good examples. What's stage 4 then?
Stage 4 is reinforcement learning, RL. This builds directly on the SFT initialized model. Here, the focus shifts to refining the agent's strategy based on outcomes in, ideally, a simulated or real web environment.
So learning from success and failure.
Pretty much. The goal is to, as they put it, internalize the agency capability, improve multi-turn reasoning, get better at using its tools, search, visit, and crucially, enhance generalization so it works better on unseen sites. It optimizes the agent's actions to achieve higher rewards.
And they use a specific RL algorithm for that. Depot?
Yes, DEPO. Decoupled clip and dynamic sampling policy optimization. The paper describes DAPO as optimizing the agent's policy, its decision-making process, towards actions that lead to higher rewards.
What about the dynamic sampling part?
That seems key. It has a dynamic sampling mechanism designed to intelligently prioritize training. It focuses more on examples the model hasn't fully mastered yet from SFT, and potentially ignores less reliable or noisy samples encountered during the RL exploration process. It aims to make the learning more efficient and robust.
How are the rewards structured in RL? Is it just about getting the right final answer?
Primarily, yes. The reward signal is a weighted sum. There's a small weight, like 0.1, given for getting the output format perfectly correct, score format, but this is mostly handled by SFT anyway.
Okay.
The vast majority of the reward, like 0.9 weight, comes from getting the final answer correct, score answer. And this correctness is again verified by that LLM as judge. So the agent is heavily incentivized to succeed in the actual task.
Why the two stages, SFT then RL? Why not just jump straight to RL? Seems simpler.
The sources, especially the paper, really emphasize that SFT provides essential behavioral grounding, that cold start. Trying to learn the complex sequence generation, the formatting, the reasoning flow, and the optimal strategy all at once, purely from sparse outcome-based RL rewards. That's apparently far less stable and efficient for these kinds of complex agentic tasks.
So SFT gives the model the basic moves, the structure.
Exactly. And then RL fine-tunes the strategy to actually win the game, to succeed on the unpredictable real web. This two-stage approach is presented as a key reason for their performance gains.
Okay, so recap. They build novel hard data using CRWLQA and E2HQA. They carefully filter example trajectories using that three-stage funnel. Then they use SFT to teach the basic React behavior. And finally, RL with DAPO to perfect the strategy for the real world based on outcomes.
That's a great summary of the pipeline.
So the big question, does this pipeline actually work? What do the results say?
The experimental results they present look pretty promising. WebDancer was benchmarked on standard tasks like GAIA and WebWalkerQA, and it showed substantial gains over the vanilla React baseline, which is basically just using prompting with React without this whole pipeline.
Better than just prompting a powerful model.
Yes, and notably, it even surpassed GPT-4o on some of these benchmarks, which is quite impressive given GPT-4o is often used as a powerful baseline itself.
That definitely suggests the pipeline is adding significant value.
And it also showed consistently strong performance on more challenging datasets like BrowseComp, which are designed to test robustness in complex, deep information-seeking scenarios.
Okay, so the scores look good. Beyond the headline numbers, what did their analysis reveal about why it works, or maybe what the remaining hurdles are?
Yeah, the analysis section has some crucial insights into the pipeline's impact. For instance, they found that RL significantly helps models that might have weaker inherent reasoning capabilities to sample correct responses more efficiently, and improves metrics like pass at 3 or consistency at 3, meaning they get the right answer more often within a few tries.
So RL helps less capable base models punch above their weight in this task.
To some extent, yes. And for the stronger base models, like larger reasoning models, RL seems to improve consistency. Even if the first attempt success rate, pass at 1, doesn't jump quite as dramatically, it makes them more reliable in the web environment.
Interesting. So RL makes weaker models smarter in this context and stronger models more dependable.
That seems to be the takeaway for these web-based tasks. The analysis also empirically confirmed the necessity of both the high-quality COLQAE2 HQA data for SFT.
Garbage in, garbage out still applies.
Right. And the necessity of the SFT cold start itself. Performance was apparently quite poor when they tried RL without the SFT initialization.
Underscoring the value of that two-stage approach. What did they observe about the agent's actual thought process after RL training? Did it change how it solves problems?
This is really fascinating. The analysis indicates that RL encourages the agents to pursue longer reasoning processes. They take more steps, essentially. And it supports more complex sequences of actions.
So it's not afraid to dig deeper if needed.
Exactly. It seems to foster the emergence of more sophisticated reasoning strategies within the model itself, because those strategies are the ones that lead to successful outcomes and rewards across multiple steps. It's not just tuning superficial behavior, it seems to be influencing the internal reasoning process.
That suggests a deeper internalization of agency, not just mimicry.
It points in that direction, yes. However, the analysis also starkly highlights the remaining challenges. A big one is the environment itself. The dynamic, unpredictable nature of the real web is a much larger source of errors and instability than, say, the internal randomness of the model's generation.
Right. Websites change layouts, APIs break, content disappears.
Precisely. The environment itself is often harder to predict or handle than the agent's own thinking process.
That's a tough problem.
It is. And another challenge they note is transferring the very complex, nuanced reasoning you might see in the largest research models, the ones they used for sampling those long code trajectories, down into smaller, more practical instruction-tuned models for the actual fine-tuning. The full depth of sophisticated thought doesn't always transfer perfectly.
The distillation problem. Okay, we've covered the pipeline, the data, the training, the results, the analysis. Let's make it concrete. Can we look at a specific example from the sources to see WebDancer's thinking in action?
Absolutely. The case study shown in Figure 8 in the paper provides a great illustration. You can really see the agent exhibiting quite sophisticated reasoning patterns for an autonomous system.
Like what kind of patterns?
Well, for instance, it demonstrates step-by-step decomposition. It explicitly outlines its plan, like, first I need to figure out X. Then I will search for Y. Finally, I will combine the information. It breaks down the complex problem.
Planning ahead. Nice.
It also performs hypothesis testing. It might make an assumption based on some initial info, maybe about who Nemo refers to in a query, and then actively uses a search action to verify or refute that assumption before proceeding.
Smart. Check your assumptions.
And it handles information gaps. If it realizes it needs a piece of information to have, like a specific zip code for a location query, it recognizes that gap and initiates a targeted search specifically to find that missing piece.
Proactive problem solving.
Exactly. And finally, it shows iterative reflection. It seems to adjust its strategy based on the observations it gets back after each action. If a search didn't work, it might try a different query or approach.
So it's not just blindly following a pre-generated script, it's dynamically thinking, acting, observing, and then refining its approach based on what happens. That feels like a significant step towards real agency.
It really does, and it speaks to the effectiveness of their whole data and training pipeline in fostering these kinds of behaviors.
Given this capability, though, what are the current limitations they themselves point to? And what's next on the research agenda?
Yeah, the sources are quite clear that this is a step forward, but there are definitely significant frontiers for future work. One major limitation is the toolset. Currently, the agent primarily uses only two basic tools, web search and visiting a web page.
Pretty basic browsing.
Right. To handle more complex real-world tasks, it needs integration with things like full browser modeling, understanding forms, buttons, interactive elements, maybe connecting to scripting environments like Python for calculations, or API interactions, using other specialized tools.
Like actually filling out forms online, or interacting with maps, or using web-based calculators.
Precisely those kinds of things. It also currently focuses mainly on relatively short answer question tasks, scaling up to handle document-level research, summarizing long texts, or generating longer form content. It's still really hard.
Especially designing the rewards for RL, I bet.
Exactly. Designing good reward models for evaluating nuanced, lengthy outputs in RL is a major challenge. Judging a paragraph-long summary is much harder than judging a single-factor number.
True. Any other big limitations?
Yes, there are computational and efficiency challenges mentioned. The RL stage, with all the environment interactions and LLM calls, is expensive and time-consuming. This currently limits the amount of collected experience data that can be effectively used for training.
So they collect more data than they can actually train on.
It seems that way due to computational constraints. They also point out the need for a hybrid thinking model, one that can dynamically choose between using short, quick reasoning chains or longer, more deliberate ones, depending on the problem. Right now, models are often trained specifically for either short or long sati.
Adapting the thinking style on the fly.
Exactly. And finally, they still encounter some what they call thinking pattern issues, things like the agent hallucinating tools it doesn't actually have, or getting stuck in loops performing redundant actions. Basic reliability issues still crop up.
Okay, so plenty of hard, fundamental research problems still ahead on the path to truly robust web agents.
Absolutely. WebDancer provides a strong foundation and a systematic approach, but these limitations really define the key directions for ongoing research in the field.
Looking at the bigger picture now, the briefing document touches on the potential real-world impact. What are the broader implications if we get really good at building systems like WebDancer?
Well, there's definitely a positive side. These agents have the potential to, democratize powerful web information access. Imagine capable open source agents assisting researchers, students, educators, or really anyone trying to navigate complex topics online.
Automating the tedious parts of research.
Right. They could significantly boost productivity and maybe even access to knowledge by automating difficult information-seeking tasks that currently require a lot of human time and effort, making deep research more accessible.
That sounds pretty transformative. But there are risks too, right?
Oh, absolutely. The sources acknowledge significant concerns. If these systems aren't built and deployed carefully, they could easily amplify misinformation. Imagine an agent synthesizing facts from unreliable sources without proper vetting or source tracking.
Scary thought.
It is. And there's also the risk of misuse, things like large-scale automated data extraction for purposes the website owner never intended, sophisticated content scraping, or even automated surveillance if these agents become very capable at navigating and extracting personal information.
So powerful tools always come with serious risks attached.
They really do. And the need for transparency in how these agents operate, clear source attribution in any information they provide, and strong responsible deployment guidelines, these are all critical considerations highlighted right alongside the technical advancements.
This has been a really insightful deep dive into WebDancer's systematic approach. We've seen how it tries to tackle the core challenges of building autonomous web agents through innovation at basically every stage of the process.
Yeah, starting with generating that novel, deep data using methods like CRWLQA and that clever E2HQA reverse construction.
Then leveraging the React framework, but adding that rigorous multi-stage filtering to create really high-quality training trajectories.
And then employing that two-stage learning pipeline, using SFT for the crucial cold start to get the basic behaviors down, and then RL with specialized algorithms like Depot to refine generalization and strategic thinking based on real-world outcomes and rewards.
It really is a comprehensive framework. It seems to address fundamental aspects of building these agents, moving beyond just clever prompt engineering.
Definitely. And the results seem to demonstrate its effectiveness as a potential new paradigm, even while the acknowledged limitations clearly map out the challenging but exciting frontier for future research in creating even more robust and capable web navigators.
So here's something for you, the listener, to consider as this technology continues to develop. If systems like WebDancer become truly capable of autonomously navigating and understanding the entire web, how might that fundamentally change the way you interact with information? How might it change how you conduct research or learn new things in the future?
And perhaps just as importantly, what new responsibilities does that place on both the creators and the users of these potentially powerful new digital assistants? A lot to think about as these agents continue to evolve.